Greetings 347 fans. This is a second video on separable first order differential equations. In the first video we saw some methods to classify and some strategies to solve these differential equations. In this video we'll have a look at a couple of different applications, namely the application of heat transfer and the application of a chemostat. Okay, so here's the first application, heat transfer, better known as Newton's law of cooling. So according to Newton's law of cooling, which also works for heating, the rate of change of a temperature of a body is proportional to the difference between the current temperature of the body and the ambient temperature, or the temperature of the environment. So you can think about perhaps a cup of coffee that's hot in a cool room, or you can think perhaps about a cold glass of water in a room that's at room temperature. Now, of course, this doesn't apply to things like phase changes. Melting and boiling are processes that are different thermodynamically, so we're not going to be discussing those. Okay, so in any case, we'll go ahead and derive a differential equation model for the temperature of this body relative to the constant ambient temperature. Now, a couple keywords here, just like before, rate or rate of change indicates a derivative, and proportional to indicates a constant times that quantity. So here, the rate of change of the temperature is proportional to the difference between the temperature and the ambient temperature. So that allows us to write down a differential equation for the temperature T, capital T, of some body relative to the constant external or ambient temperature T sub E. T prime equals H times the quantity T minus T sub E. Now, just like before, this is a good opportunity to give our model a sign check. So what happens if capital T is smaller than T sub E? So capital T smaller than capital T sub E would be like the cold glass of water in a warm room. In this case, we would expect that the temperature of the cold glass of water would be an increasing function, but it looks like in our model, T minus T sub E in that case would be negative, possibly making that temperature a decreasing function. Similarly for T greater than T sub E, that's the cup of coffee at room temperature. In a room at room temperature, we would expect the coffee to be a decreasing function so that its derivative ought to be negative. So similarly here, our model sort of has the backward interpretation. So there's an easy fix for this. Just go ahead and hit your model with a minus sign. We'll go ahead and write capital T prime equals negative H times T minus T sub E. And then just require that the constant H, the constant proportionality, be a positive number. In this case, our model acts like it ought to, and gives us the correct behavior. Okay, so this differential equation is separable. It happens to also be an autonomous differential equation, and for autonomous differential equations, we can describe equilibrium solutions. So I'll remind you that an equilibrium solution is a constant value that satisfies the differential equation. We find those by looking for the right-hand side of the differential equation equal to 0. So you should be able to see that when capital T is equal to T sub E, the right-hand side is 0, and of course the derivative of T is 0, and we can see that both sides of the differential equation are satisfied. That is, when we substitute capital T equals T sub E, it turns our equation into an identity. So T equals T sub E is a solution. And again, the interpretation here is that if your glass of water is already at room temperature, so the temperature of the water is equal to room temperature, then we don't expect that temperature to change at all. And our model supports that idea. Okay, so we can go ahead and solve this with separation of variables, and I'll go ahead and formally separate variables to write the integral of 1 over T sub E, T minus T sub E dt equals the integral of minus H dt. That's again using our shortcut to the chain rule. The left-hand side looks like a natural log, and the right-hand side integrates up just like a first-order polynomial in T. Of course, we can undo this natural log by exponentiating and identify the explicit solution, the explicit family of solutions, I suppose, as this function capital T of t is capital T sub e plus some constant times e to the minus ht. And again, having a look here at our model, it appears that as t gets infinitely large, time, that is, as little t gets infinitely large, capital T approaches T sub e, which is something we would expect from the model, whether we have a cold glass of water or a hot cup of coffee. If we leave it in some room for a long time, it ought to approach room temperature. Okay, so this is the famous proper pint of bitter problem. A proper pint of bitter should be served about 55 degrees Fahrenheit. The local pub has a room temperature of 70 degrees Fahrenheit, and the refrigerator temperature is measured to be 40 degrees Fahrenheit. So 5 minutes after pouring, we see that the temperature of the pint is 45 degrees Fahrenheit. And the question here is, how much longer do we have to wait until our pint is at the proper temperature? That is, how much longer until the temperature reaches 55 degrees. So we assume Newton's law of cooling here, where capital T of t is the temperature of the pint of bitter. So we just saw that the solution, in the case of Newton's law of cooling, is capital T of little t equals T sub e plus a constant times e to the minus ht. Temperature of the environment, or the ambient temperature here, T sub e is given by 70. Now it turns out that this initial temperature gives us enough information to solve for the constant of integration capital C. So here T of 0 equals 40, so it had better be that 40 is equal to 70, the ambient temperature, plus constant times e to the 0, so that tells us that the constant capital C is equal to 30. Now we know one more bit of information in this case. We know 5 minutes after serving the temperature is 45 degrees Fahrenheit, which allows us to solve for the rate h. So on one hand, T of 5 is 45. On the other hand, 45 had better be equal to 70 minus 30 times e to the minus 5h. So that quantity 70 minus 30 times e to the minus 5h is just our solution, capital T of t, where we've substituted in T sub e, c, and little t equals 5. So similar to our exponential decay problems, we can use properties of exponents and logarithms to identify the constant h, which turns out to be 1/5 times the log of 6/5. So finally, we hope to find the time when the temperature is 55. So here we'll go ahead and set that time t star to be an unknown time, and the temperature at t star had better be 55. So again, using properties of logarithms and exponents, we can identify that that time is 1 over h times the log of 2, and it turns out that plugging that into your calculator gives about 19 minutes. Okay, so in reference to how much longer we'll have to wait, the answer is about 14 more minutes. And just for completeness here, we see a few different solution curves. We see one starting when time is 0, starting at 40. We see a few others too. Of course, ours, which starts at 40 when time is 0, passes through 45 at time 5, and we can see that it hits that temperature of 55 degrees after about 19 minutes, so 14 more minutes after 5 minutes. Okay, so the last application in this section is an application on chemical reactors or chemostat problems. In this scenario, we define a chemostat. So a chemostat is a well-defined volume to which a chemical in solution enters. Possibly there's a reaction, and then the chemical exits. So one important assumption that we'll discuss often in this model is that the chemostat is well stirred, so that the concentration is uniform throughout the volume. Okay, so the idea here is that that chemical enters at some flow rate Q and some concentration Cn. Possibly there's a reaction, and then the concentration leaving the tank is the same as the concentration throughout the tank. Okay, so again, that's the well-stirred assumption that the concentration leaving the tank is the concentration throughout the tank. So we can derive a differential equation for this model by asking ourselves how the mass of chemical in the chemostat changes. Okay, so on one hand, the mass of chemical in the chemostat ought to be the volume in some cubic meters times the concentration in the chemostat in some sort of grams per cubic meter. Okay, so quantity in meters cubed V times the quantity in grams per cubic meter C will give us a mass in grams G. Okay, similarly, the rate at which mass flows out is going to be the rate at which mass flows in is the flow rate in Q times the concentration in, and the rate at which mass flows out is the flow rate out Q times the concentration out, which again is just the concentration throughout the tank, capital C. So the rate at which mass changes, that's square bracket VC prime, is equal to Q in C in minus Q out C. Okay, so again, here we're taking those rates Q to be the same so that the volume in the tank is constant. Okay, so just like before, a quick sign check. What do we expect to happen if the concentration in the tank is greater than the concentration coming in? So in that case, we would expect the concentration in the tank to be decreasing, or the mass of chemical in the chemostat to be decreasing, and we can see that's true. And in this case, if the concentration in the tank is less than the concentration coming in, so that there's a stronger chemical coming in, we would expect the mass of chemical in the chemostat to be an increasing function, and we can see that's the case for C less than Cn as well. Okay, so this ends up being a perfectly good initial value problem that's separable in the case where we assume that the flow rates in and out are the same Q, and there's some initial concentration C naught at time 0. So in addition to being a separable differential equation, this differential equation ends up being autonomous, and similar to last time, we can find the equilibrium solution. Here we see that the equilibrium solution is C equal to Cn, and the interpretation in that case is that when the concentration in the tank is the same as the concentration coming in, we wouldn't expect the concentration in the tank to change. That makes sense. Okay, so we can solve this initial value problem with separation of variables, and I'll go ahead and run through that quickly. We can see that that C prime is minus Q over V times the quantity C minus Cn. And here we'll go ahead and use definite integrals in the fundamental theorem of calculus to identify an implicit solution to the initial value problem. That's the log of the quotient there is equal to minus Q over V times T. Okay, so the explicit solution to this problem is sort of similar to the one that we saw in the case of Newton's law of cooling, and no doubt the differential equation is very similar as well. The explicit solution to the initial value problem is given by C of t equals Cn plus the quantity C naught minus Cn times e to the minus Q over Vt. Okay, so a couple of things here. We can see pretty quickly that this quantity satisfies the initial condition. If you substitute t equals 0, we can come up quickly with C of 0 is C naught. And similarly, as t goes to infinity, as time gets large, the exponential term vanishes, and we see that the limit as t goes to infinity of C of t is equal to Cn, which makes sense also. After a long time, the concentration in the tank should be equal to the concentration coming into the tank. And again here, this is a perfectly differentiable function on the interval minus infinity to infinity, so that's the interval of existence for the solution of this differential equation. Okay, so here is an example of a tank mixing problem. A large mixing tank holds 300 gallons of water in which 50 pounds of salt have been dissolved. Okay, so that information actually gives us an initial concentration, right, 50 pounds in 300 gallons. A brine solution is pumped into the tank at a rate of 3 gallons per minute, and well-stirred solution is pumped out also at 3 gallons a minute. So we can see that the volume in the tank is constant. The flow rate in and the flow rate out are both 3 gallons per minute. So we'll find the amount of salt in the tank if the concentration of the solution entering is 2 pounds per gallon. Okay, so we can see that the concentration entering at 2 pounds per gallon is less than the initial concentration, which is 1/6 of a pound per gallon. So we'd expect the concentration in the tank increases over time. Okay, so we'll go ahead and identify the initial value problem. And here it is, right? C prime is minus Q over V times C minus Cn, where C of 0 is C naught. And again, this is due to the fact that the flow rate in and out are the same, that constant Q. Okay, so the other parameters of the problem are V equals 300 gallons, Cn is 2 pounds per gallon, and C naught is 1/6 pounds per gallon. Okay, so we go ahead and solve this initial value problem just as we did previously. The solution is C of t equals Cn plus the quantity C out minus Cn times e to the minus Q over V times t. So we see the solution here, and we can see, as we expect, it satisfies the initial condition and it has the correct behavior as time goes to infinity. So for what it's worth, here are a few different solution curves, including one that starts at concentration 0, one that starts at our concentration in red of 1/6, and a few others, including one that starts at concentration 2. And again, the interpretation, if we start at concentration 2 and flow in brine with concentration 2, is that things shouldn't change, and that's what we see here as well. Of course, if we start with a higher concentration in the tank than the concentration coming in, we see that that concentration is a decreasing function of time, and all of those different concentrations approach to concentration 2 as time increases, as expected by our model. Okay, so we'll end with a couple variations on these chemostat models that end up not being separable differential equations that we'll have a look at later. So here's the first generalization. We'll assume that the inflow and outflow rates are not equal. So we're going to go ahead and assume that the rate flowing in is maybe something like Q in, and the rate flowing out is something like Q out, so that the volume is variable too. So there's a change in the model in this case, but we can derive a new model by, again, tracking the rate at which the mass of chemical in the chemostat changes. Okay, so once again, the mass of the chemical in the chemostat is going to be given by V of t times the concentration. And here I'm going to write V of t specifically as a function of t to indicate that it's not constant. The rate at which mass flows in is Q in C in. The rate at which mass flows out is Q out times C. And we kind of use the same idea that the rate at which mass changes is the rate in minus the rate out. There's a typo on the slide. It should say Q out times C, not Q in times C. And again, the volume in the tank is V sub 0 plus Q in minus Q out times T for some initial volume V naught. Okay, so this ends up not immediately being a separable differential equation because of that quantity V of t, but we'll see how to deal with this differential equation in section 1.4. Okay, a second variation on this model is to imagine a scenario in which case the inflow and outflow rates are back to being equal, but there's a reaction in the pond, a degradation reaction, by which the mass of chemical degrades at a rate proportional to the amount of chemical in the pond. So again, here we have a couple of familiar terms. A degradation at a rate proportional to the amount of chemical. Okay, so we'll again track the rate at which the mass of chemical in the pond changes, and here we see that the mass of chemical in the chemostat is given by Vc, going back to writing V as just the constant value because the flow rates in and out are equal. The rate at which the mass flows out is Q times Cn. The rate at which mass flows in is Q times C, again because of this continuously stirred reactor or constant concentration assumption about the mass in the tank. We take the rate out to be Q and the concentration out to be the concentration in the tank. And then again, the rate of degradation, the rate is proportional to the amount of chemical in the pond, which the amount of chemical in the pond is just given by V times C. Okay, so this gives us a new differential equation model. V times C prime is Q times Cn minus Q times C minus R times the quantity V times C. And actually, as it turns out, this differential equation does end up being separable. So there's a challenge there to solve this by separation of variables and try to see what the effect of that extra reaction in the pond is. Okay, so that's it for part 2 of separable differential equations. I hope you have fun watching this video, and we'll go ahead and discuss this more in the upcoming days. Thanks for watching, and we'll see you next time.